Hello, my name is Keval Shah and today I'll be talking about the parallelization of matrix multiplication. You can see that the topic is divided into two segments. Parallelization is a type of optimization technique, whereas matrix multiplication is a mathematical operation and it is a problem domain. Let me first discuss about parallelization. So parallelization is the concept of using your hardware capabilities of your system. The systems around us, the computers that we use, even the local machines, the supercomputers and the computers that are used in day-to-day activities for hosting servers and things like that, each of them is a multi-core machine. We have come in an era in which a normal CPU is at least 4 cores and a normal GPU is at least 60 cores. Now starting off with the concept of cores. Most of the basic operating system operations are done on single cores. Whereas when we do mathematical operations, we do computations, those are done on multiple cores. Now, why would we want to use multiple cores? Why do we need to write different code for parallel system? Why do we need to use expensive hardware? The reason is that it's very fast. If you have 2 cores and you write a perfect parallel code, you can finish your job in half the time. So let me explain this with an example of a task. Suppose I have a task T and I compute it in time theta. Now if I am running this on a single processor, it will take time theta naught. If I run the same task using P processors, my task will be divided into T by P segments and each will be given to a single core of the machine. Hence, this will also reduce my execution time to theta by P. So you can see that what clear difference it is making. Scientists are working on problems and simulations that take almost months to run. Now imagine if we use a multi-core system and write good parallel code, and say with a system of 60 cores, we can reduce the time taken in months to a mere few days. Now let us move on to the problem domain. Since you must have studied matrix multiplication in your early linear algebra and maths classes. Suppose I have a matrix A and I have a matrix B. Now I want to multiply matrix A and B and store the result in matrix C. The correct idea would be to traverse through each row of A and multiply it with each row of B to get that corresponding element. For instance, if I want to get the element C is 1, 0, that is this element, I would traverse through the first row of A, and 0th column of B. And then I would dot product the corresponding cells and add them up to get this value. Now you can clearly see that this operation is independent of the other rows and the other columns, and this can be performed independently. So if I distribute the elements of C among P threads, then that would mean that I can distribute the total time required to do the multiplication among P threads, and the total time required to do the multiplication will be reduced by P times. So I have used the purple marker for indicating the task done in time step 1, green for indicating the task done in time step 2, and red for indicating the task done in time step 3. And let us say that I have 3 cores or threads. I will use these terms interchangeably. Generally, each core will launch a single thread, and we can use them interchangeably. Now, for this first time step, suppose thread 1 will calculate this, thread 2 will calculate this, thread 3 will calculate this. and 1 will calculate this by doing the row multiplication of A into row multiplication of B, and so on. Now I come to the next time step. For the next time step, thread 1 will calculate this element, thread 2 will calculate this element, and thread 3 will calculate this element. Similarly, this element is received by doing this multiplication. And for the final third step, I can see that I will complete my entire process. Thread 1 will do this, thread 2 will do this element, and thread 3 will do the last element. Once again, this element is received by doing this multiplication. You can see that the total time steps was just 3 in parallel. If I try to do this serially, the time steps would be 9. Hence, the time taken has clearly decreased by a factor of 3, and 3 is the number of cores. Now let us do a time analysis on the time taken for matrix multiplication. Matrix multiplication takes time of the order of m cross m cross m, where m is the length of side of matrix A and B. C is equal to A cross B. Let me call the serial time as Ts. Like from previous analysis, we found that the parallel time was Ts divided by P, where P is the number of cores or threads. This value, when we replace by the value given here, comes down to m cubed by P. Hence, we can see that this parallelization is so scalable that if we increase the number of processors, the time decreases linearly. Thank you for watching my video. Have a good day.